When we did potential energy diagrams, we talked a little bit about enthalpy, but here is the formal way to calculate it, a little bit more in depth. When you break a bond, which is what happens to our reactants in any reaction, you're breaking those bonds. Well, not any reaction, but most reactions. You require energy. You have to add energy. However, when you form them, you release energy. And that's sometimes hard for students to get behind because it seems like forming something requires you to do work which requires energy. But you have to remember that atoms want to bond because they become more stable. And when they become more stable, they can just kind of release some of that energy, release some of that tension. So when they become more stable, when they bond, they will release energy. So when you're talking about delta H or change in enthalpy, you know it's energy of products minus energy of reactants. If it is positive, we know that that means it's endothermic. And so that also means that the breaking of the bonds required more energy than was released when the new bonds were formed. So overall, you had to add energy. Overall, it was an an endothermic reaction. If delta H is negative, that means the forming of new bonds released more energy than was required to break them. So you know overall energy is released. That is an exothermic reaction. So delta H is negative. We also have a concept that's different from enthalpy, which is entropy. Entropy is randomness. So a lot of times you will hear it's disorder, randomness, anything like that. It's actually the formal way of thinking is that it is a measure of how spread out energy is in a system. This is kind of nice because energy is attached to particles. So if the particles are more spread out, then the entropy is higher. The entropy increases. When left alone, a system will always move towards spreading out its energy. And you've seen that a whole bunch. Like if you spill something on a counter, okay, it spreads out. It travels around the counter. That is because the system is increasing its entropy. If you have a balloon that's not tied, or you have a balloon that is tied and then you pop it, or you let go of the little enclosure, all the air will come out of it because it wants to be spread out more. That is an increase in entropy. So there are many times you have seen this. So when entropy increases, that means it is more spread out at the end of a reaction. When it decreases, that means the energy is less spread out at the end of a reaction. A favorable change in entropy is S. So a favorable delta S would be positive because it means that the products have more entropy than the reactants. And we just said, left alone, something is going to increase in entropy, like the air that leaves the balloon. So a positive delta S is favorable. Negative delta H is favorable. So if you have a negative change in enthalpy, meaning the reaction's exothermic, that's favorable because we didn't have to add any energy. But delta S is favorable when it's positive. So this is a little bit kind of counterintuitive, but we're going to get to that in just a minute. So let's focus on entropy for right now. These are really the three principles of entropy. Entropy increases as the particles spread out in a phase change. So as you go from solid to gas, or liquid to gas, it's going to go up. They're more spread out. Entropy increases if you create more moles of gas. So we're just going to be looking at gas for this one, meaning if we have 2 moles of gas on one side and 3 moles on the other, that's an increase in delta H. And that's what's happening here. You look at the coefficients for moles. So you have 2 moles and they're gas. And then you have 3 moles, they're both gases. So that's an increase in S, increase in entropy. And then if you increase the temperature, you are also increasing the entropy. So let's look at a couple of examples here. For this number 1, does entropy increase or decrease in the reaction? Now you can answer this one of two ways. You're going to get the same answer. But you can see that it goes from gas to liquid. So you know that that means the particles are closer together. So delta S would be negative, meaning entropy decreased. You could also look at moles of gas, which is what we're going to rely on a lot. Here you have 1 mole of gas, and here you have 0 moles of gas. So that's an entropy decreasing. So either way you look at it, your entropy is going down. So now taking a look at this one, we go from 2 moles of gas to 1 mole of gas, looking at just the coefficient. So this is also going to have a negative delta S. Entropy decreases. This slide we'll go over in class. If you want to try the practice, you can pause it here. And then I'll put the answers up for you. So all of these increase in entropy, delta S is positive, except the last one. The last one, we go from 2 moles of gas to 0, so that's going to be a decrease. So that brings us to something called spontaneous. So what we said was negative delta H is favorable, positive delta S is favorable. That relates directly to spontaneity. A spontaneous process is something that happens on its own. You don't have to intervene. You don't have to do anything to it. To figure out whether a reaction is spontaneous or not, what we do is we use a formula called Gibbs free energy formula. The Gibbs free energy formula is going to be delta G, and I'm going to show you the whole formula on the next slide. But delta G, if it's negative, the reaction is spontaneous, meaning it will just happen on its own. And if delta G is positive, it is not spontaneous. You would have to do something else to make the reaction happen. So in this formula, you're going to have some delta H, you're going to have some delta S, and then we also have to take into account temperature. Okay, I already wrote this. So here we have delta G, which is the change in Gibbs free energy. And it can be in either kilojoules or joules, it doesn't matter. But you need to have, and we're going to talk about this in a second, you need to have delta H and delta S be in the same unit because they're subtracting. So here we have change in enthalpy. You have temperature, which must be in Kelvin. And you have delta S, which is going to be your change in entropy. It doesn't matter if delta H and delta S are in joules or kilojoules, unless the question specifies, but they do need to be in the same units. And that is something you need to pay very close attention to. So when you're doing this, if you get a negative number, then it's spontaneous. If you get a positive number, it is not spontaneous. And that is why you will see this minus sign, because remember delta F, if it's positive, it's favorable. Okay, so then the negative sign takes care of that. So all you have to do is plug in the numbers you know and see if delta G comes out to be positive or negative. I want to take a minute to go over converting joules per Kelvin to kilojoules per Kelvin, because this joules per Kelvin is a lot of times what you will see delta S in for its unit. But you want it in kilojoules per Kelvin so that you can subtract with delta H. The nice thing is you don't have to change the Kelvin. So all you have to do is take the joules into kilojoules. So all you have to do for that is take your decimal point and move it back 3 spaces. So this would be 0.543. Now be careful, because sometimes your delta S will be given to you in kilojoules, and then if you move it back 3 spaces without thinking, you're going to get it wrong. So make sure you're just paying very close attention to the units. But as long as you get the units right, this formula is very easy and straightforward. So let's do an example. A reaction has a delta H of negative 28.8 kilojoules and delta S of negative 54.0 joules per Kelvin. So I see right away that I need to change this. Because I need to have kilojoules and kilojoules in order to do that subtraction. So is the reaction spontaneous? There are a couple ways that you can think about this, but the easiest way is to just plug it into the formula and see what you get. So delta G is equal to delta H minus T delta S. Delta H is negative 28.8 kilojoules. And then you're going to subtract our Kelvin times our delta S. So you'll see that the Kelvins will cancel, and then you'll have kilojoules minus kilojoules. So when we do out this part, the subtraction part, you got to do the second part, the T delta S first. You get 28.8 kilojoules minus, plus, because it's minus a negative, plus 16.092 kilojoules. That comes out to negative 12.7 kilojoules for delta G. But that's not what the question is asking. The question is asking, is it spontaneous? So you have to actually answer the question. It's not asking for the value of delta G. Sometimes we will, but this time we're not. So we say, yes, it is spontaneous, and that is our answer. And so that's the Gibbs formula. That's all you have to worry about.